In this lesson, we will continue to focus our attention on cache organizations. And so we've explored two cache organizations thus far. Fully associative cache, which we just introduced, has its benefits. It's the most flexible, but it's also the most, requires the most hardware complexity. With our direct map cache, it's fairly simple to implement, but it's also not as flexible as a fully associative cache. And so this presents us with the problem. Can we do better in terms of the cache strategy that we utilize? And is there a compromise? And unfortunately, there is a compromise. We call it a set-associative cache. And so it turns out that direct mapped and fully associative caches are just degenerate cases of a set-associative cache. And most caches that we have are set-associative. And so let's compare. In our direct map cache, we have n rows within our cache that are utilized. With our fully associative cache, we have various blocks that are essentially going to be equivalent to n rows, but these are going to be in parallel. So now with a set associative cache, we want to have parallel caches, but also have them with rows. And so in this form, we have n over p rows with p parallel caches being utilized. So this provides us with a trade-off between a fully associative and a direct map cache. And so this organization is based off of us being able to have a memory block that is going to be associated with a set of appropriate cache blocks. And so let's take an example of how we could utilize or compare the different versions of our caches. So with our direct map cache, you want to keep in mind that we have n lines within our cache. We have a valid bit, a tag, and then our data. Then we can compare a two-way set associative cache. We could have two parallel blocks with each containing 7 entries within the cache, 8 entries within the cache. So in this regards, we have 2 blocks in parallel, each containing 8 entries that can be retrieved from the cache. We can also have a 4-way set associative cache. So in this case, we have 4 parallel blocks and each cache containing 4 lines. So this provides us with a quick way to understand the types of set associative caches that we can utilize. We can have the 2-way cache, or we can have the 4-way cache. But some things to consider is that we need to check the same line in each of the blocks in the cache to find our data. So if we want to compare what's required to look up the data in the cache with our direct map cache, it requires a 4-bit index to look up the value in the cache. with our two-way set associative layout, it requires just 3 bits in order for us to look at the value that it's going to be in the cache. And with our 4-way set associative, it's just going to require us a 2-bit index. So if we have the memory address, we're going to have to look up all the possible spots within our cache set. So now let's keep in mind, and so in this case, again, we have to check the memory block in 2 places and then the memory block in 4 places in parallel. So let's keep in mind some terminology that we need to be sure to consider. So we have essentially 4 different ways of saying the same thing when it comes to terminology. It can be confusing, but different documentation will use these terms interchangeably. And so when we're talking about a cache entry or a cache line or cache block, they're all meaning the same. You can refer to it as a cache line, a cache block, a cache entry, or a cache element. All of these terms mean the same thing and the basic unit of data that is being transferred in or out of the cache at a time. And so a cache set is a row in the cache, and the number of blocks per set is determined by the type of cache utilized. And so with this in mind, we have some generalizations that we can consider. You want to consider that a direct map cache has n sets and 1 element. A p-way set associative cache is going to have n over p sets and p elements, while a fully associative cache will have 1 set with n elements. So if we can consider this for our generalization for the 2-way set associative, if you recall, we said it'll have n over p sets with p elements. So if we compare a direct map with a 2-way, we have 8 sets of 2 elements that are being utilized here. And in this case, we have 4 sets of 4 elements for our 4-way set associative cache. And so in order to implement our 4-way set associative cache, we're essentially going to need to build 4 caches. And in this regard, we're going to have 4 comparators. And then we'll have our AND gate that's going to be looking at our valid bit to check. And then we have our multiplexer that uses our interrupt priority to determine which value gets put out first. And so essentially to implement our set associative cache, we're going to have to build P sets of caches that are going to be utilized. And so an example with our 4-way set associative cache, we have a 32-bit memory that's byte addressable. We have 64 kilobytes within our cache size. A word contains 4 bytes. The block size is going to be 16 bytes. So 4 words. We have an appropriate write-through policy, and we have 1 valid bit per block. So we have our 4 caches here in parallel. our memory address. So we have 1K entries. We use our offset, we use our index to select the value from the cache. Our offset is 4 bytes, and our tag is going to be 18. So with the cache block size, if we have 16 times 8, that's going to give us 128. To be the size of the data that we have in our cache entry. And so if we were to compute the total amount of storage that we need, we're going to sum up the value for each required for each entry, 1 plus 18 plus 128. We're going to multiply that by the number of the size of our cache times 4 divided by 8. So it's going to give us 75,264 bytes to be the total amount of storage that we need in order to implement our cache. So in this way, we've introduced a compromise for our cache organization with set-associative caches. The hardware complexity that we need, how many comparators are we going to need for our cache? And in this case, we're going to need 4 18-bit comparators that we're going to need to utilize. So let's consider in a fully associative cache with 64 kilobytes of data, 64 bytes per block, and with a T-bit tag, there are going to be how many comparators? 4 T-bit tag comparators, 64 T-bit tag comparators, 1K T-bit tag comparators, or there's going to be 1 T-bit tag comparator for the entire cache. You'll want to recall that with the fully associative cache, we're going to need a comparator for each of our caches. So in this case, we're going to need at least 1K T-bit tag comparators for our cache, for a fully associative cache. So let's also consider if we have a 4-way set-associative cache. It has 64 bytes of data, 64 bytes per block, with a T-bit tag. How many comparators will we need? Will we need 4 T-bit tag comparators, 64 T-bit tag comparators, 1K T-bit tag comparators, or 1 T-bit tag comparator for the entire cache? And so if you recall from our previous example, we needed P comparators based off of a P-way set-associative cache. So that means that we know that we're going to need at least 4 T-bit tag comparators for our cache. So in this lesson, we've wrapped up introducing appropriate organizations for a cache. Next, we will explore how we're going to be able to handle our cache replacement policies, as well as how they are utilized, how the cache can be utilized with our translation look aside buffer. Which you recall, our TLB is just another mechanism as a cache.